Yes, sir.
Okay, right. Good evening, everyone. Thanks to IMA Chennai South for this nice opportunity. And this is the 6th webinar in the History of Medicine series. A special thanks to Dr. Ramakrishnan, the state IMA president, who despite his pressing commitments is always there to encourage academic activities. And my thanks to Dr. Maragati Madam and Shanta Naram Madam and other office bearers of the IMA South. This webinar series has acquired its sheen by the presence of Professor V. Mohan, the most accomplished diabetes specialist of our nation. My job has been to collect the relevant material and make a presentation to you all. It is his words of wisdom at the end that puts everything in the right perspective. Thank you very much, Professor Mohan sir, for your presence. History always gets neglected in most conferences, unless it is an important occasion, like a centenary year for some discovery or some occasion to remember. Otherwise, we don't give much importance to history. Even in reputed textbooks, you can see the first chapter will be on history, but that all the scientists' lifetime work will get a passing mention within a sentence or two. It is my great privilege and honor to do this presentation, which is a tribute to the Nobel laureates, who through years of painstaking work has made the life of our patients easier. You can see 6 people in this first slide. The first two are Henry Bragg and Lawrence Bragg, father and son duo. The third one is Fred Sanger. Fourth is Dorothy Hodgkin. Fifth is Rosalind Yalow. And sixth is Bruce Merrifield. None of them was a medical doctor. And that is probably another reason for us not celebrating them as we do for the discoverers of insulin. Once insulin got discovered, the biggest problem in 1922 was to maintain the life-saving supply to rapidly expanding markets. Though companies like Eli Lilly and Novo Nordisk made great contributions by commercially manufacturing insulin, there was always the danger of running short of the crucial supply, that is the animal pancreas. You can see in this picture a big mound of pancreas in the Lilly plant, Eli Lilly plant in US. To produce 1 pound of concentrated insulin crystals, you can see in the picture, there is a small bottle kept there in front of the mound of pancreas that contains the insulin crystal, the white structure in the bottle. So to produce 1 pound of that concentrated crystal, they required 10,000 pounds of pancreas. It soon became obvious that there was an acute need to find ways to industrially produce synthetic insulin urgently. And then George Minot developed type 1 diabetes in 1921. This may be something which is not connected to the previous slide, but still there is a connection. I will come to that later. He developed type 1 diabetes in 1921, and he was one of the very early patients to receive insulin in the United States. He later won the 1934 Nobel Prize for medicine for his discovery that liver extracts improved pernicious anemia. The cause for pernicious anemia was a shortage of vitamin B12 found in the liver. The discovery made it imperative that the structure of vitamin B12 should be detected urgently to produce it in a mass scale. So there was an urgent need for production of vitamin B12 as well as insulin. When World War started around the same time, in the 30s, there was an urgent need for mass production of the newly discovered penicillin. With this background in mind, let's move away from the University of Toronto to the lab of pure scientists. This is because that's where the true journey of modern medicine began. Röntgen discovered X-rays and was awarded the very first Nobel Prize for Physics in 1901. Even though it was immediately adopted to clinical use, a lot of hospitals started using X-rays to detect, injured bones or foreign bodies and whatnot. So they rapidly it was started used by the hospital setting, but no one tried X-rays in other fields until Max von Laue came. Max von Laue won the Nobel Prize for Physics in 1914 for his discovery of the diffraction of X-rays by various crystals. You can see the original X-ray diffraction image captured by him, various images. The figure 1 shows copper sulfate. Copper sulfate was the very first crystal which he studied, and its diffraction pattern is shown in figure 1. Henry Bragg, a famous physics professor in UK, read Law's paper, became fascinated by the unique diffraction pattern of each crystal. Henry Bragg devised a spectrometer to generate X-rays and record the diffraction pattern in photographic plates. This is a spectrometer devised by Henry Bragg. He captured the pattern of common salt and showed the photographic plate to his son, Lawrence, who had just graduated in physics. Lawrence, an intelligent guy, immediately saw a puzzle there and guessed what the solution was. Henry Bragg, his father, had already showed that the molecules or atoms in a crystal are arranged in an absolutely regular pattern. The atoms are arranged in planes, various planes, and each plane acts as a semi-transparent mirror. The X-rays are reflecting off the various planes and are bouncing in all directions. He realized that the X-rays are being bounced by the planes, and with this, he can detect where the atoms are within the crystal. Both Henry and Lawrence proposed a law of diffraction, which is known as Bragg's law. Father Henry collected the data meticulously, and son Lawrence interpreted the data and arrived at the results with complex calculations. The father and son were very successful in detecting the structures of various crystals. The first structure which they detected was of common salt, because that's the one which was easily available, the crystal. So they found the structure of the common salt first. When Nobel Prize was announced, Lawrence Bragg was in a trench fighting the German army during World War I. In a trench, he heard that he was awarded the Nobel Prize Award. So Lawrence Bragg was the youngest winner of the prize at the age of 25. Of course, Malala became the youngest winner later on when she won it for peace. There was double delight for Lawrence, as the telegram informed him that he, along with his dear father, were together chosen for the physics prize for the year 1915. Within that caption, you can see a Nobel Prize for Physics 1915 awarded to you and your father. They are the only father and son duo to receive the prize in the same year. The prize was awarded for their meticulous analysis of crystal structure by means of X-rays. What the senior Henry Bragg kickstarted as a field of crystallography, it has landed 29 Nobel Prizes to date and still counting. This is one of the fields which has netted the most number of Nobel Prizes till date. And Henry Bragg was a great teacher, and he enjoyed giving physics demonstrations for young school children. Even after winning the Nobel Prize, he interacted with school children a lot. This was one of the lectures given by him for school children, and he wrote books for children also. You can see in this photograph how he is at home enjoying his time with children. He is demonstrating the diffraction pattern of a crystal there, and look at the children enjoying his lecture. Now let's move on to Dorothy Hodgkin. Dorothy Hodgkin from Cambridge University was awarded the Nobel Prize for Chemistry in the year 1964. This is the first Nobel Prize after Banting and Best prize for insulin. Her award citation read, "Determination by X-ray techniques of the structures of important biochemical substances," which included insulin. As a young girl, she studied in a boarding school in England as her parents were working in Africa. During a visit to Africa in one of her holidays, she found a shiny black mineral in the farmyard in their home. Looking at her enthusiasm around the crystal, a visiting family friend, Dr. A.F. Joseph, a very famous soil scientist, gave her a box of reagents and encouraged her to analyze it. As luck would have it, she received another important present, a book on X-rays and crystal structure for school children by Henry and Lawrence Bragg at the age of 16. After reading the book, she was captured for life by chemistry and crystals. Now I think you can understand the connection between Lawrence Henry Bragg and Dorothy Hodgkin. Hodgkin remembered a sentence from the book that read, sorry, before that, let me just go through this slide. So in her times, when she wanted to do chemistry instead of home science like other girls, she had to petition the school authorities because it was the norm of the day that girls will study home science and boys will go for the other branches. So she had to petition the authorities to get into the class. Dorothy and her close friend Nora were the only girls in the chemistry class, and you can see them experimenting together in the back row. You can see them within that highlighted area. And at the age of 18, she joined Oxford to study chemistry, another first in those times. You can see young Dorothy here with two of her male classmates in Oxford University campus. For PhD, she joined the lab of Dr. J.D. Bernal, a famous chemist who headed the Cavendish laboratory at Cambridge. Bernal himself was a student of Henry Bragg. Again, Henry Bragg influenced so many people. So Bernal was a student, and Bernal was a self-declared communist who believed in equal opportunity for women. It so happened that Bernal photographed the X-ray of a protein crystal. It was a momentous feat as it was the first proof that organic molecules can be crystallized. Once you get a crystallized form of an organic molecule or biological substance, you can always pass X-ray through it, get diffraction image, and analyze the structure of the atoms and molecules within that sample. This possibility of crystallizing biological specimens paved the way for studying them with X-ray diffraction. This landmark discovery was published in Nature journal in 1934. The second author in that paper was young Miss Dorothy, along with Dr. Burser. This was the first X-ray hydrated pepsin crystals taken by Bernal in 1934, together with Dr. Dorothy. This was the first glimpse of the molecular world that underlies the living things. This was the first specimen of a biological sample getting photographed as a crystal. Dr. Bernard continued training young crystallographers from his Cavendish laboratory. It was poorly funded because of his open support for the regime of Stalin. Because he was a communist, naturally the authorities in UK disliked him, so his laboratory was not funded properly. Because of his preoccupation with active politics, many promising projects got stalled. His trainees netted 5 Nobel Prizes in the next 2 decades, completing what Bernal started. Not winning a Nobel Prize never bothered him and was aptly called as the sage of science by his students. In this, you can see in the slide that there was a book published by one of his students where he is called the sage of science. In this photograph, you can see Bernal with Sir C.V. Raman and other Nobel laureates from his Cavendish lab. After finishing her PhD under Dr. Bernal, Dorothy joined Oxford as a chemist and crystallographer. At the very young age of 24, she developed rapidly debilitating arthritis and was literally confined to a wheelchair for her movements from her late 30s. So she used to come to the lab in her wheelchair, and she was given a small lab in the ground floor because she cannot climb stairs. Despite her limited hand movements and constant pain, she produced intricate drawings which were vital for her work. Though she started her work with insulin first, you can see on the right, the first paper about insulin crystal published by Dr. Dorothy, but then this work got interrupted because of the pressing need for mass production of penicillin, a miracle antibiotic during the Second World War. It took 4 years for Dorothy to solve the puzzle, and in 1943, she successfully made this model of penicillin. You can see that original model by Dr. Dorothy. This is a penicillin model. Let me just rapidly discuss the steps in structural determination of a protein crystal using X-ray crystallography. The first step, obviously, is to grow pure form of the protein crystal. So you need a biological sample. You crystallize the sample first. So it can take weeks and even years to get a pure crystal. Once the crystal is available, put it in an X-ray spectrometer, shine the X-ray through it, and capture the diffraction data. Up to this level, Bragg's came. With the diffraction data, electron density maps were drawn, which we're going to see how Dorothy elegantly did it. Final steps require atomic model calculations. That is very complex. The first step is to fire the X-rays at a crystal. The crystal diffracts the X-rays to create a pattern on a detector. And these are the diffraction images on the photographic plate. The first step from this is to draw an electron density map from the diffraction data. Each contour ring drawn by Dorothy here is an atom. If an atom has multiple rings, it has higher electron density and vice versa. You can also see the bonds between the atoms. Dorothy painstakingly drew the map by hand on a perplex sheet with a marker pen. Perplex sheet is a clear, transparent acrylic sheet. Remember, she has got severe arthritis, and that she had to draw all the more sheets were drawn for every successive slice through the molecule, which is akin to a CT scan pattern. So for every plane, she drew a model and then arranged it. The sheets were placed in rectangular stand like this, one above the other. Now imagine the transparent box created by successive perplex sheets disappear like this, and you are viewing only the contours.
Mandate to the points.
Can you unmute? Can you mute?
Yes, sir. I'll try to. I'll mute everybody, sir.
Yeah.
Okay. I think you are the host, sir. You mute everyone, sir. I'll reclaim my host. Host.
Okay. Anyway, I'll continue.
You can mute everyone and then unmute yourself alone. One second, I'll reclaim my host.
It's okay, ma'am.
Open pudu pack. Hello, use it only after some time.
Hello, please mute yourself. Whoever it is, please mute yourself.
Okay.
Hello.
Okay, ma'am. Now I'll proceed, ma'am.
Sir, host sir, I will do it.
Stop sharing.
No. Stop sharing. என்னோட பேர் பக்கத்துல மோர்னு இருக்கும் பாருங்க, அந்த இடத்துல அத கிளிக் பண்ணனா போஸ்ட் மாத்தலாம்.
I'm not able because I am handling a MacBook, ma'am. It might be difficult.
Okay, no problem. You continue, sir. Okay.
So now you can see the transparent box created by successive perplex sheets disappearing, and you are viewing only the contours drawn by the pen. If the contours get filled by opaque color, you can see the molecule surface. With this model, the bonds between the atoms can be inferred. Now it is easy to see. You can see the models getting assembled here. And now it is easy to create a ball and stick structure, which we normally see in chemistry labs. This is a structure of penicillin created by Dorothy Hatch in the World War II era. It took 4 years for her to map the structure and spatial arrangements of 17 atoms. For vitamin B12, which contains 181 atoms, she took 8 years to map and completed it in 1956. Eventually, after 34 years of hard work, with a team of assistants, in 1969, she conquered insulin with its 788 atoms. Was her junior colleague at Oxford, who was awarded the Nobel Prize for Chemistry in 1962 for discovering the complex structure of hemoglobin. You can see the structure of hemoglobin there. He was very embarrassed to hear the news that he got the prize ahead of Dorothy. He was awarded the Nobel Prize 2 years ahead of her. He said with all humility that Dorothy had made great discoveries with fantastic skill and chemical insight and had always preceded his own. When Dorothy finally got the Nobel Prize 2 years later, the British press was not so impressed like Max Perut about her academic credentials. The headline screamed, "Nobel Prize for a British wife," thus shifting the focus on her duties as a mother of 3 children rather than her role as a teaching professor at Oxford and a visionary, deeply revered research scientist among her peers. it still remained a men's world, starting from her school chemistry days to her becoming a Nobel laureate. Dorothy was the second woman after Florence Nightingale to receive the Order of Merit. She encouraged young talents from China and India. She fought the system which was against graduate women who decided to marry. She donated a portion of her Nobel Prize money for starting a child care center at Oxford, thus helping young researchers with and to continue their work without interruption. You can see her standing with Dr. Stephen Hawking here. When she was awarded the Nobel Prize, PM Margaret Thatcher invited her for a dinner. Dorothy was her physics professor in college. So Dorothy was in fact her professor and taught physics for her. Dorothy Hodgkin was bestowed with a great mind and an amazing talent. She was an exceptional leader and an impeccable role model for future generation of crystallographers. The crystallography work, which Dorothy accomplished in 4 to 5 decades of work, can be accomplished in days to weeks now. The protein. So, before moving on, I just want to touch upon this. This is the photo 51 of Rosalind Franklin from the University, King's College, London. Actually, Rosalind was a crystallographer working in King's College, and she took this photograph. And this photograph 51 was shared by one of his distant colleagues with Dr. Crick, who was visiting Rosalind, and Dr. Crick actually copied this, drew this picture in the newspaper which he was carrying. And then they realized that this holds a clue for the helical structure of double helix structure of DNA, and then they later on devised the structure of DNA. And until Rosalind died, she never knew that the spark for the double helix model was from her photograph 15. So we can do a separate webinar on this topic alone. And the proteins studied today are far more complex and require highly specialized facilities. One such lab is a diamond light source in Oxfordshire. It has synchrotron, a particle accelerator that can generate beams of light 10 billion times brighter than the sun rays. It has particle accelerator ring that can accelerate electrons close to the speed of light. It can analyze crystals as small as 5,000th of a millimeter of a size. Complex structures of viruses and receptors like this are getting unraveled. And this is the modern X-ray spectrometer.
Wait, now I know what Karima is saying.
The Indian scientist working in diamond light source, Venkatraman Ramakrishnan, was awarded the Nobel Prize for Chemistry in 2009 for the discovery of structure and function of the ribosome. This was a Nature's cover story on ribosome, and you can see how complex it is when compared to the structure of common salt discovered by Bragg. You can see on top the structure of common salt. Compare it with the structure of ribosome by Venkatraman Ramakrishnan. We will know the difference. And this is the way we have come, like from common salt, a simple structure by Bragg, to lysozyme to ribosome. We have come a long way. And NASA has actually rover to Mars. It is called Curiosity rover to Mars to analyze minerals in Mars. And this machine carries a crystallography spectrometer. So we have reached Mars. The crystallography as a science has reached Mars. Let's move on to Frederick Sanger of UK, who won the Nobel Prize twice for chemistry in 1958 and 1980. When Sanger was a biochemistry student, the Second World War was raging. He was against the war and preferred to work as an ambulance driver rather than getting enlisted as a soldier like Lawrence Bragg. He was the product of the famous Department of Biochemistry in Cambridge University, which routinely produced Nobel laureates. You can see how many Nobel laureates are there from this single department. While Dorothy zeroed in on the actual atomic structure of insulin, Sanger was responsible for the identification of the amino acid sequences of the insulin molecule. With the help of acid, he broke the insulin molecule into smaller parts. With electrophoresis and chromatography, he separated them from one another. He then determined the sequences of 51 amino acids in the molecule chains. He also identified how the two chains are linked together by two disulfide bonds. When the 1958 Nobel Prize in Chemistry was awarded to him, he richly deserved it. Here you can see Sanger posing the complex atomic model structure of insulin in the Cambridge lab on the right. The Times, the paper, described his achievement as a biochemical equivalent of a 4-minute mile, a great feat achieved by Roger Bannister a year earlier in Oxford. Later, Sanger moved to the more modern Medical Research Council Laboratory of Molecular Biology. His research focus shifted to DNA, and he was awarded the Nobel Prize in Chemistry for the second time in 1980 for his determination of the nucleotide sequences of the DNA. The Laboratory of Molecular Biology, headed by Fred Sanger, produced a long list of Nobel laureates like his alma mater, Cambridge Biochemistry Department. Again, you can see the number of Nobel laureates from Fred Sanger's laboratory. Later, the huge Wellcome Funded Institute was named in his honor. In the year 2020, that is last year alone, this institute was responsible for 568 publications in reputed journals. Because of his contributions, Sanger is celebrated as the father of genomics. And this was the house where he lived. You can see the plaque on the wall of his house. And this is his biography written by George Brownlee. To know about the last two Nobel laureates in this webinar, let's cross over the Atlantic to North America. Rosalind Yalow was awarded the 1977 Nobel Prize in Physiology or Medicine, even though she was a nuclear physics professor, not a medical doctor. So without being a doctor, she received a Nobel Prize for Medicine. Yalow hailed from a poor family. She had to work as a part-time stenographer to a biochemist in return for attending 3 classes in nuclear physics at the University of Illinois. So parents were very poor, they couldn't afford the fees. So she worked in the same university in a different department as a stenographer and attended the classes of nuclear physics. And she joined the same university later as a faculty. She was the only woman in a faculty strength of 400. You can imagine the number of women in science around that time, 1 out of 400. At 26 years of age, she got a PhD in nuclear physics and joined the Veterans Administration Hospital to develop radioisotope service. Rosalind met Aaron Yalow when she was a student at the university and later married him. At the VA hospital, there was a rule that women had to quit the job at 5 months of pregnancy. Rosalind fought the system and stayed on. Later, she remarked that the only difference between men and women in science is that the women have the babies. This makes it more difficult for women in science, but is merely another challenge to be overcome. Nuclear physicist Yalow was joined by Dr. Solomon Burson, an internal medicine specialist, to take care of the patient-related aspects of the department. Both learned from each other, and their 22-year partnership was broken only by his death in 1972. Yalow and Burson used radioisotopes to measure blood volume. That's how they started first. Soon they shifted to insulin as a purified form of insulin was easily available at that time. So insulin was available as a crystal. That's why they zeroed on insulin. Then Yalow has also a personal reason to choose insulin, as her husband Aaron had diabetes and she was determined to do some research in that area. Yalow and Burson attached radioactive iodine to insulin and injected into volunteers, including themselves. They injected radioactive iodine labeled insulin into themselves and measured insulin levels with a Geiger counter. Using immunoassay, she and Burson had shown the presence of insulin antibody in the blood of insulin-treated patients, a very first in the history. This finding ran very much contrary to the 1950s view that immune system cannot recognize small proteins like insulin. Science Journal rejected the paper in 1955, and so did the Journal of Clinical Investigation. With further research and a subtle change in the title by removing the words insulin transporting antibody, both of them finally succeeded in getting the landmark paper published in 1956. On the right, you can see the rejection letter sent to the first author, Dr. Solomon Burson, by the editor of the Journal of Clinical Investigation. Radioimmunoassay, or RIA, used radioactively tagged substances to measure antibodies. RIA has the capability of detecting extremely low concentration of substances down to a billionth of a gram. In her 1977 Nobel lecture, Yalo herself listed over 100 substances like hormones, vitamins, enzymes, viruses, drugs, etc., that could be precisely measured. RAA revolutionized a lot of things, which include antibiotic therapy. We can measure the viral load now. All hepatitis B patients measure the viral load, and plays an important role in infertility treatment and so on. When her colleagues asked her to patent RAA, she refused to do so and said, patents are about keeping things away from people for the purpose of making money. We want others to be able to use it. That's her character. ADA in 1961 awarded the Eli Lilly Award to Yalo and Burson, recognizing their combined work in the RAA area. Burson died in 1972, 5 years before the award of Nobel Prize to Yalo. As Nobel Prize cannot be awarded posthumously, Burson did not become a Nobel laureate. Yalo did not forget to mention this in her Nobel lecture. I want Yalo continued to work till her old age. And she said, the excitement of learning separates youth from old age. As long as you are learning, you are not. And I want to mention few interesting facts about the mentor of the last laureate, Bruce Merrifield. Dilworth Wayne Woolley was a Canadian born in Alberta, like Colin, who purified insulin. Both of them were born in Alberta, Canada. As a child, Woolley had severe rickets and recovered from treatment with cod liver oil. In the early 1920s, he developed type 1 diabetes and was saved by Banting's insulin in 1923, like George Minot, 1934 prize winner. He later became the head of Rockefeller Institute of Medical Research in New York. He became completely blind by 25 years of age due to diabetic retinopathy and vitreous hemorrhage. He had photographic memory, and once his assistants read journal articles aloud for him, he will remember everything, including page number and paragraph. He isolated vitamin B3 and pantothenic acid. He was a pioneer of serotonin hypothesis and is considered the father of field of antimetabolites. Woolley married a bacteriologist, Janet McCarter, 8 years his senior. Janet was a professor in University of Wisconsin. Janet sacrificed her own promising career to support Woolley. According to experts, the world had lost a brilliant bacteriologist because she was working a lot on tuberculosis around that time. The world could have easily lost the genius of Woolley's without the support of his wife. That also is true. Shortly after receiving his PhD, he became completely blind. At Rockefeller, his wife and assistant spent hours reading journals to him every day, and he used to remember. His home workshop had no lights installed. He used his pointer so well during presentations that no one could tell that he was blind. He had photographic memory. And his first paper on serotonin hypothesis was rejected by Lancet. This is a book written by Dr. Woolley, The Biochemical Basis of Psychosis. Actually, one of the main pillars of psychiatry today is serotonin hypothesis. And then Bruce Merrifield arrived at the Rockefeller Institute in 1949 after graduating in biochemistry and microbiology. Bruce joined as a postdoctoral fellow under Dr. Woolley. While working in the lab of Dr. Woolley, he realized that there was a need for a more efficient rapid synthesis of peptides. When Bruce started experimenting with solid phase synthesis, he was given 3 months' time by his chief, Dr. Woolley, to get some publishable results. Experiment after experiment failed, and he would declare to his graduates that he was going to hit and open a gasoline station on the road to Arizona desert. Fortunately, he never carried through on that desert, right? But the work consumed 3 years to produce a simple tetrapeptide, and Bruce was always grateful to Woolley, giving him the freedom to pursue the problem through a long, non-productive period. In such big reputed labs, if you are not publishing 2 or 3 papers every year, you will be chucked out. So Woolley was persistent, and he gave him almost 3 years' time. Bruce became the head of Rockefeller Institute when Woolley died in 1966 at the age of 52 years due to heart attack. Bruce, as a lab head, was non-dictatorial, non-intrusive, and was always accessible for his colleagues. What are the steps in solid phase peptide synthesis and how it is different from the previous methods? the solution synthesis of a pentapeptide, Bruce, 11 months, and his yield was a very poor 7%. In the solid phase method, the last amino acid is attached to a solid resin support. So imagine a long chain of peptide, and you take the last amino acid and attach to a fixed solid. Then you couple the next amino acid to the main chain with the help of a coupling agent. So you attach this amino acid to the first amino acid. This process is repeated until the peptide chain is elongated to the desired length and constitution. All the chemical steps building the amino acid sequence is carried out in an automated synthesizer. During each step, impurities are washed away by mechanical processes. The final product is cleaved from the solid resin support, purified by HPLC, and then lyophilized to form a fluffy white powder. This is how we get the peptide. Solid peptide synthesis is 20 times faster and allows the preparation of longer peptide chains. So remember, insulin is a long chain. It has a long chain. That's how the solid peptide chemistry was very important to prepare synthetic insulins. And now, just to simplify this, you just imagine a long garland is being made. You can see this garland is hanged on a solid support, and the garland maker makes small pieces of garland and keeps attaching it to the garland. Imagine Bruce attached each amino acid to the previous one like this, and then got the long chain. And this was the first paper published by Bruce about solid phase synthesis in 1963. And this was the first paper by Bruce and his colleague about insulin. Along with his first graduate student, Garland Marshall. Actually, Garland Marshall worked a lot on the insulin synthesis, and Bruce was directing him. So both of them together formed a series of increasingly larger peptides, and then the jewel in their crown was a synthesis of bovine. Bruce's work was recognized by the Nobel Committee in 1984. Remember, he published his work on insulin in 1963, but only in 1984, finally, the Nobel Prize Committee recognized his work, and they decided to award the 1984 chemistry prize to him. So biochemistry was known as animal chemistry in 1900s. There was widely quoted saying, "Tear chemi is sheer chemi," translating into animal chemistry. But today, biochemistry, nuclear physics, and crystallography lie at the crossroads of frontier research in the field of modern medicine. Much of the progress in medicine was made possible by these branches of science. Banting, West, MacLeod, and Coleb brought insulin from bench. That means they formed the insulin, purified it, and took it to the bedside of Leonard Thompson to give that first injection. But then these four people, the phenomenal research by Fred Sanger, Dorothy Hodgkin, Rosalind Yalow, and Bruce Merrifield, took insulin back to the bench again for further refinement, without whose contribution we wouldn't have used insulin as easily as we do today in modern medicine. They have individually fought all odds, like the Second World War, physical disabilities, poverty, gender bias, and whatnot, to pave the way for science to progress. Thanks for patient listening, and I apologize for the background.